This world is not what you think it is. This world is not what you think it is.
Is that called Scientism, when you believe so much in the science you've been taught that you refuse to believe something else and it becomes your religion in a way?
Yes, Scientism is where people turn science into a kind of religion. It becomes a kind of dogmatic belief system. The irony is that a lot of people think that religion is dogmatic and science is free thinking, but actually, in my experience, some of the most dogmatic people I know are people who've made science into a kind of religion.
The idea was to hang by a very, very fine quartz fiber a rod with two balls, and then put two large lead balls in the positions indicated here next to it on the side. Then, because of the attraction of the balls, there would be a slight twist of the fiber. It had to be done so delicately because the gravitational force between ordinary things is very, very tiny indeed. And there it was. And it was possible then to measure the force between these two balls. Cavendish called his experiment weighing the Earth. We're pedantic and careful. Today, we wouldn't let our students say that. We would have to say they're measuring the mass of the Earth. You know? But the reason he said that is the following. By a direct experiment, he was able to measure the force and the two masses and the distance, and thus determine the gravitational constant. You say, yes, but we have the same situation on the Earth. We know what the pull is, and we know what the mass of the object pulled is, and we know how far away we are, but we don't know either the mass of the Earth or the constant, but only the combination. So by measuring the constant and knowing the facts about the pull of the Earth, the mass of the Earth could be determined. So indirectly, this experiment was the first determination of how heavy or how massive is the ball on which we stand. It's a kind of an amazing achievement to find that out, and I think that's why Cavendish named his experiment that way instead of determining the constant in the gravitational equation. Weighing the Earth. Oh. He incidentally was weighing the sun and everything else at the same time, because the pull of the sun is known in the same manner.
Things like the gravitational constant, the speed of light, are called the fundamental constants. Are they really constant? Well, when I got interested in this question, I tried to find out. They're given in physics handbooks. Handbooks of physics list the existing fundamental constants, tell you their value. But I wanted to see if they'd changed, so I got the old volumes of physical handbooks. I went to the Patent Office Library here in London, and they're the only place I could find that kept the old volumes. Normally people throw them away when the new values come out. They throw away the old ones. When I did this, I found that the speed of light dropped between 1928 and 1945 by about 20 kilometers per second. It's a huge drop because they're given with errors of only fractions of decimal points of error. And yet, all over the world, it dropped, and they were all getting values very similar to each other with tiny errors. And then in 1945, it went up, 48, it went up again. And then people started getting very similar values again. I was very intrigued by this, and I couldn't make sense of it. So I went to see the head of metrology at the National Physical Laboratory in Teddington. Metrology is the science in which people measure constants. And I asked him about this. I said, what do you make of this drop in the speed of light between 1928 and 1945? And he said, oh dear, he said, you've uncovered the most embarrassing episode in the history of our science. So I said, well, could the speed of light have actually dropped? And that would have amazing implications if so. He said, no, of course it couldn't have actually dropped. It's a constant. So, well then how do you explain the fact everyone was finding it going much slower during that period? Is it because they were fudging their results to get what they thought other people should be getting, and the whole thing was just produced in the minds of physicists? We don't like to use the word fudge. I said, well, what do you prefer? He said, well, we prefer to call it intellectual phase locking. So I said, well, if it was going on then, how can we be so sure it's not going on today? And that the present values are produced by intellectual phase locking. And he said, oh, we know that's not the case. I said, how do we know? He said, well, we've solved the problem. And I said, well, how? He said, well, we fixed the speed of light by definition in 1972. So I said, but it might still change. He said, yes, but we'd never know it because we've defined the meter in terms of the speed of light. So the units had changed with it. So he looked very pleased about that. They'd fixed that problem. But I said, well, then what about big G, the gravitational constant known in the trade as big G? It's written with a capital G, Newton's universal gravitational constant. That's varied by more than 1.3% in recent years. And it seems to vary from place to place and from time to time. And he said, oh, well, those are just errors. And unfortunately, there are quite big errors with big G. So I said, well, what if it's really changing? I mean, perhaps it is really changing. And then I looked at how they do it. What happens is they measure it in different labs. They get different values on different days, and then they average them. And then other labs around the world do the same, and they come out usually with a rather different average. And then the International Committee on Metrology meets every 10 years or so and average the ones from labs around the world to come up with the value of big G. But what if G were actually fluctuating? What if it changed? There's already evidence, actually, that it changes throughout the day and throughout the year. What if the Earth, as it moves through the galactic environment, went through patches of dark matter or other environmental factors that could alter it? Maybe they all change together. What if these errors are going up together and down together? For more than 10 years, I've been trying to persuade metrologists to look at the raw data. In fact, I'm now trying to persuade them to put it online on the internet with the dates and the actual measurements and see if they're correlated, to see if they're all up at one time, all down at another. If so, they might be fluctuating together, and that would tell us something very, very interesting. But no one has done this. They haven't done it because G is a constant. There's no point looking for changes. You see, here's a very simple example of where a dogmatic assumption actually inhibits inquiry. I myself think that the constants may vary quite considerably, well, within narrow limits, but they may all be varying. And I think the day will come when scientific journals like Nature have a weekly report on the constants, like stock market reports in newspapers. You know, this week, big G was slightly up, the charge on the electron was down, the speed of light held steady, and so on. That's one area, just one area where I think thinking less dogmatically could open things up.
In 1797, Henry Cavendish, the British scientist, Freemason, and wealthy grandson of the Duke of Devonshire, created an experiment which he claimed successfully proved the existence of gravity, measured its constant, and provided accurate figures for the exact masses of the Earth, Sun, Moon, and planets. How did Cavendish achieve this quantum leap for heliocentric pseudoscience? He fixed two large lead balls on opposite ends of a torsion balance and hung them from the roof of his shed. By watching and recording slight motions of the contraption via telescope through his shed window so his mass would not affect the reading, Cavendish claimed to have proven gravity. Two small lead balls were hung near the large ones, and any motion observed towards one another was touted as being the influence of gravity. Now, the Cavendish experiment has been widely criticized by the scientific community because never in over 2 centuries since its creation has anyone been able to replicate it. Firstly, the balls simply do not always attract one another, as they must, for the so-called gravitational constant to be constant at all. Sometimes the torsion balance turns towards the balls, and sometimes away, as it is impossible not to give some slight tremulous motion when interacting with it. Henry even complained in his notes how often as he was performing the measurement, the contraption was still in oscillation. Secondly, since his calculated force of gravity was 10 to the 39th power weaker than the force of electromagnetism, from which all material objects are composed, there is no control for the experiment, which can factor out and positively differentiate the alleged gravitational force from the known, stronger electromagnetic force. In other words, the balls could simply be attracting each other through static electricity, a known force existing in all things, billions of times stronger than gravity, and impossible to control for the experiment. Even though no one could replicate Cavendish's findings, the experiment went down in history as a great success, and is still taught as veritable proof of universal gravitation in science textbooks today.
One of my favourite scientists is Henry Cavendish. Even though he was part of the rich Dukes of Devonshire, that family, and incredibly rich, he went to Cambridge to study natural sciences, or natural philosophy as it's called. But he had a very curious condition in that he could hardly talk to anybody. So when it came to his Viva exam after 3 years of study, he fled Cambridge rather than sit in front of the examiners because he was petrified of them. But he was one of the most brilliant scientists of that 18th century in both chemistry and physics. For chemistry, he's noted because he analysed gases in the air. He discovered there was hydrogen, which is a huge component of the universe. He called it inflammable air. So he put some acids in a container, dropped some metal like zinc into hydrochloric acid, and got the gas to come off. And then to show it was inflammable, you could set light to it, he breathed it in and blew it into a candle. Now, do not do this at home, because it blew up and took all the hairs off his face. He invented the idea of electric potential before everybody else, and used to set electric currents through his body to work out the voltage was proportional to current, and he measured the current by the degree of agony he felt with the electrical current. This is not the normal sort of person. He couldn't talk to most people. He couldn't talk to women at all. His housekeeper would get a recipe for something or other, and he'd say, no, lamb tonight, leg of lamb, and leave a note for her. He wouldn't say it, he'd write it. He would dine in the evening with his friends, and he would talk to them, but if he didn't know somebody, and you wanted to ask him a question, apparently you had to go to the Royal Society, and he'd be in the room, and you'd address the room this question about physics, and you postulate, and if he felt in the mood, he would reply to the room. He was a very strange man, and yet he's absolutely wonderful. He invented hydrogen. People went up in hydrogen balloons and could see the world through that perspective. He did most of the experiments quietly on his own, keeping his notebooks, and it was only after his death and a persuasive campaign by Clerk Maxwell, the famous Maxwell of Maxwell's equations from Cambridge University, that he actually got the notebooks from the estate of the Dukes of Devonshire and discovered after the event that Cavendish had discovered the unit of capacitance, discovered dielectric constants, he discovered Dalton's law of partial pressures, he discovered or written about Coulomb's law, all before these guys had done it, and just left it unpublished in his notebooks. Towards the end of his life, he did a crucial experiment, which is represented by these lead balls. He lived in Clapham Common, which is nowadays a very poor part of London, but there it was quite fashionable. And he built his own place. His library he built somewhere else because he didn't want anybody borrowing his books from his house. Otherwise, he would have to ask the book back and he didn't want to talk to them. So his library was 4 miles away. At the back of it, he had a big garden shed, which might seem like the size of my house. And in it, he had 2 lead balls, like this, suspended from the ceiling. Only this is not to scale. This is, lead balls. Now, the real problem is that he wanted to measure the attraction between 2 objects due to gravity. In other words, there's a gravitational attraction between you and me, or between me and this lead ball. So he had to be a long way away to look at the experiment, otherwise he'd interfere with it. So he had an aperture, a place where he could look through, and he put a telescope out there, and he stood outside in all weathers, and he was in his 60s doing this, staring through the window to take his measurements over a year. There's another set of lead balls inside there. This experiment really is very difficult to get to work, and a technician has sawed it apart because he got so frustrated. And then right in the middle there's a bit of glass, there's a mirror which should be suspended from a torsion wire. So you'd set it up like this in his shed, and you put it like that, and this lead ball would attract that lead ball, and this lead ball would attract this one, and so it would be pushed a little bit this way and twist the wire, and that would be pushed a little bit that way, and the wire would twist, and as the wire twists, the mirror, which is dangling in there, would twist a little bit, and light which comes in would be reflected off at a slightly different angle, and all he had to do was measure the angle. He then had to move it the other way round. Oh, he didn't move this bit, he moved the lead balls round so that you had an equal and opposite effect on the other side. So instead of having, you have that configuration. He had this is a very complicated technical thing for the time. 18th century we're talking about, and he put that way round, and then it was pushed the other way, and you could then see the displacement. Moreover, you could measure the period of oscillation of this, and from that get all the properties of the wire, the torsional constant. And that enabled him to measure big G, the gravitational constant, to an accuracy of 1%. And nobody improved on that for 100 years. He didn't describe it as that. He described it as though he was weighing the Earth. He was calculating the mass of the Earth, so that when you're attracted to the Earth through gravity, it's the product of the mass of the Earth, this big gravitational constant, divided by r squared, the radius of the Earth squared, which we normally know as acceleration due to gravity. And that quantity is essentially big G, and he measured it. And nobody could do a clever experiment. So he's a father of physics, experimental physics, some of the ideas of theoretical physics, and a lot of...
Bueno.
Los naranjos.
Bueno, yo me entiendo. Jesús me mandó el cocinero por la noche a las 2 de la noche.
Pero te conviene que te entienda alguien más porque para eso cobras.
Ah, bueno, que está arriba. La sa del agua de la playa.
Abajo, los espectadores.
Espectadores, la sa que te echa a la playa.
Eso es.
No es lo de Semana Santa que los naranjos. Y Risita, coge las 20 paelleras, las amarra y las entierra en el agua. Y acuérdate, a donde las echa, que mañana tienes que ir a por ellas. Y cuando salgo, era las 2 de la noche, había bajado la marea. Las dejé amarrar, tal como me lo dijo, las tiré, le puse un palo. Dice, llego a la cocina, eran las 2:30 de la noche. Risita, ¿qué la has hecho? Allí ya está, jefe. Ya, pues acuéstate, que mañana a las 8 te llamo para que vayas a recoger las paelleras. Y me acuesto Jesús, ya para abrir el restaurante que era el arroz. Y me llama el cocinero. Risita, ¿qué? Ve por la paellera. Venga, que las 2 de la tarde ya están aquí. Miren, bañador, en las chanclas. Todo despeinado porque no me dio tiempo nada ponerme las chanclas y el bañador. Voy a la playa, había subido la marea. Jesús. Jesús. Había subido la marea y encontré una paella. Y la encontré porque estaba la paellera agarrada metida entre las piedras de Chipiona, del faro. Y cuando entro en el restaurante me ve el cocinero con una paellera y a ver la 20 paelleras. ¡Asómate, mira dónde llega el agua! Llegaba el agua hasta el restaurante. Había subido la marea. Jesús, hay que hacer ahora con los 2 sacos de arroz. ¡Ay, llama para Sevilla! ¡Llama a Sevilla que traigo paella! ¡Ay, Jesús, yo con el bañador y con la paella! ¡Ay, el cocinero! No vea, para Sevilla. Y al último, que cuando ya salió la bien de regla, estamos llorando los dos. Me cobró el tío la... Me cobró a 500 veces. Y ya no fui más. Me fui andando a coger los amarillos hasta hoy. Me mandó por la noche, había bajado más el agua y por la mañana había subido. Cualquiera estaba donde está la paellera, ¿sabes? A lo mejor está en el barco ese del petróleo.
En el Prestige.
En el Petriense. Y ya no trabajé más la cocina. Ya aborrecí la cocina. Ay, ay, ay. Pues no cobré nada, me dieron el dinero del bote.
¿Había mucho dinero en el bote?
Lo que me echaban y el dinero de lo que gané, me cobraron 20 paelleras. A 500 caras, pues viste lo que me llevé yo para Sevilla. Ay, ya aborrecí la playa. Hemos llorado los dos. Ya está, tú, no es para tanto, yo. A ti yo no quiero arroz, Jesús, yo no quiero arroz ni en chino, vamos.
Is that called scientism, when you believe so much in the science you've been taught that you refuse to believe something else and it becomes your religion in a way?
Yes, scientism is where people turn science into a kind of religion. It becomes a kind of dogmatic belief system. The irony is that a lot of people think that religion's dogmatic and science is free thinking. But actually, in my experience, some of the most dogmatic people I know are people who've made science into a kind of religion.